So in this video I want to go over a few properties of a new Poncelet family design, derived from the Steiner Porism. Let's start talking about the Steiner Porism first. So this is a well-known mathematical object, known classically, and it basically consists of a chain of circles that are mutually tangent, pairwise, and they basically glide around this inner circle here and are contained by an outer circle. So we call this inner circle the inner-Soddy circle and the outer one the outer-Soddy circle. And these blue circles here are 5 circles on this n equals 5 chain. This chain could be n equals 4. For example, here's a chain with 4 circles, which I can animate as well. Okay, you can have n equals 6 circles. There's an actual easy construction based on the inversive image of a regular system with circles. Well, that's not germane to this video. Now let's go back to n equals 5, like right here. And I want to talk about another degree of freedom of this chain, okay? And this has to do with a particular choice of inversion center, which is not being shown here. But when you actually slide the inversion center in the inversive preimage of this family, okay, you can actually go back all the way to, say, the regular version of it itself. So you can see here that the center of the outer Soddy is almost concentric with the center of the inner Soddy. Let's make them exactly concentric like that. And then we can actually visualize what's happening to what the preimage of this looks like. So actually, if I were to draw a polygon between these vertices here, and I believe I can do that by simply doing that, okay, I'll be getting a regular polygon, a regular pentagon in this case. Okay, now let's go back to the asymmetric case where I actually slide the centers of the two Soddy circles are no longer coincident. And let's look at what happened now with that pentagon. That pentagon has become a Poncelet family inscribed in an ellipse and circumscribing a circle. Now the foci of that outer ellipse are precisely the two centers of the inner and outer Soddy circle. So let's see this in motion. Okay, and of course the center of this outer ellipse here is the midpoint between the foci. Okay, now I have another center here, which is the center O prime of the caustic to this family, which happens to be a circle. Okay. Now, interestingly, if I actually were to draw the family that is, so notice that the contact points between the sides of this orange family, which we're actually, by the way, calling the Steiner-Soddy Poncelet Porism, right? This is a Poncelet Porism, okay? But I want you guys to take note of the contact points of the sides of the orange family with its caustic. They are happening precisely at the touch points between consecutive pairs of blue circles in the Steiner chain. Now, these contact points are classically known to form what's known as a harmonic family. Okay, so this is also a Ponceletian family, the magenta polygons. This family actually has as a caustic the so-called Brocard inellipse, which is not shown here. The simulation is not drawing it currently. But imagine that there's a vertical ellipse here. In fact, yeah, I believe this is going to be a vertical ellipse. And this ellipse would be the caustic of the harmonic family, whose vertices lie at the contact points of this chain. Okay, now I want you guys to take note of a couple of recent results. Let's go ahead and place them up here. Okay, it turns out that the magenta family, the harmonic polygon family, conserves the sum of its internal angle cotangents. Okay, so here's the sum of internal angle cotangents. Here's the sum of internal angle cotangent squared, cotangent cubed, cotangent fourth, and cotangents to the power of 5. Okay, now I want you to notice what's happening here. the sums of powers of cotangents up until n minus 1, and in this case n equals 5, they're being conserved by the magenta family. We've shown this in a recent paper, and I'm going to leave a link in the description. Now, interestingly, our Steiner-Soddy family, which is this family of polygons, ellipse inscribed and circle circumscribing family of orange polygons, whose vertices are the centers of circles in the Steiner chain, that is conserving a different quantity, the sum of tangents of the half angles, to a power of k, where k is less than n. So let's look at this chain of 5 numbers here. You can see that the first 4 numbers are actually staying put, while the last one is varying. Now, what do these numbers represent? This is precisely, this first number here, the sum of tangents of the half angles of the orange family, and tangent to the power of 1. Here's square tangents of the half angles, cubic tangent, or tangents to the third power of the half angles, to the fourth power, and to the fifth power. So you can see here that all are conserved except for the last one. Okay, now I want to show you guys one last set of observations. Right now, the Steiner chain is such that the center of, let me say this correctly, okay? The center of this circle here, of this caustic, is external. Perhaps I said this wrong, right? I want to say that is the center of the ellipse. Let's actually remind myself. Yeah, so that I was actually saying it right. So the center of the caustic, O prime, shown over here, okay? The caustic to my Steiner-Soddy Poncelet family. Or I can also say it this way, okay? If the center or the circumcenter, okay, of the magenta family, if that circumcenter O prime lies in the interior of the inner Soddy circle, okay, everything behaves as we're seeing here, and I'm going to vary that a little bit. So I'm going to make the circumcenter here of the harmonic polygon, or the center of the caustic of my Steiner-Soddy orange, continue to be interior. Now you can see here that as I do this, let's scale this down a bit, my outer Soddy circle is becoming bigger, right? So let's keep sliding O prime to the right, like that. So my outer Soddy circle is becoming bigger, and everything continues to work. Okay, I have 5 circles in the chain, they're mutually tangent, except that the ellipse here is becoming more and more eccentric. The outer Poncelet conic to the orange family is becoming more eccentric. So let's continue this march of, and what am I doing here? I'm actually moving O prime, the center of the caustic, closer and closer to the inner Soddy circle, to the edge or to the circumference of the inner Soddy circle. Okay? Now I'm going to get to a point now where O prime is on the edge. Now guess what's going to happen to the outer ellipse of this Ponceletian family? Okay? As it becomes more and more eccentric. Let's keep increasing that. At some point, this focus here is going to shoot off to infinity. Okay? And this family, this ellipse here, this outer Poncelet family ellipse, degenerates to a parabola. So let's watch that. And I know when the degeneracy happens, because at that point, yes, the drawing of the parabola becomes polygonized. And that's because I have a numerical problem. I'm not changing the way I'm treating or estimating these conics. So right now I'm sort of in a degenerate situation. Okay? But what you have now is a pretty interesting situation. Let me actually get out of the degeneracy a little bit so that we can illustrate this with a bit more stability here. Okay? Now let's animate this family. Now you can see here that not only has the orange family become parabola inscribed, okay, and ignore this little jump here to the left. It's because I'm sort of slightly away from the degeneracy. If I go back to the degeneracy like that, it's not going to jump anymore. Yes. But look at what happened to the outer Soddy circle. Let's scale out. The outer Soddy circle is now a straight line. And the straight line is parallel to what can be imagined here as the directrix of this parabola. Right, so the axis of the parabola is running here through the center, through F1 and O prime, and F1 continues to be the center of my inner Soddy circle. But at this degenerate situation, the other focus, which used to be here on the right, has shot off to the right to infinity. And that is the other focus of this parabola. So remember, a parabola has one of the foci on the line of infinity. Now simultaneously, the outer Soddy circle has degenerated to a line. So let's go back to prior to the degeneracy. I had this nice ellipse, I had this outer Soddy circle, and then as I cross over to the degeneracy, the outer Soddy becomes a straight line. And what happens if now O prime is pushed to the exterior of the inner Soddy circle? The outer Soddy circle is gonna evert. So it's gonna evert to a hyperbola. So let's go that way. I'm everting, I'm everting, I'm everting. Sorry, I said it wrong. The outer Soddy circle has now everted to a stationary circle, which is still tangent to the 5 circles in the chain, but it's actually externally tangent to circles or internally tangent to circles, depending on where I am on my orange family. So notice here that there are 2 phases to the orange family, right? There's a phase where all the vertices of the orange family lie on this branch of the hyperbola. And there's a phase of that family where 4 of the vertices, here's 1, 2, 3, 4, lie on this branch, while the 5th one, a lone branch, lies on the other, a lone vertex lies on the other branch. Notice that the 2 vertices of the hyperbolas continue to be centers of the inner and outer Soddy circle. Okay. Now projectively, everything here is basically the same. These are sort of Euclidean interpretation of what's going on. Let's say, I wanted to say something else here. Yeah, so what is a criterion such that the 5 vertices lie on one branch, or you have the other combinatorics, which is 4 on one branch and 1 on the other. So let's see if we can spot that criterion. It's actually pretty clear. Notice what is happening to the magenta family. Notice how if the center O prime of the caustic, okay, to the orange family, which is a circumcircle of my harmonic magenta family, if this center O prime is exterior to the magenta family, okay, I am in this 1,4 combination. When that O prime becomes right here interior to the magenta family, now I am on a, let's call this 0,5 combination. So I have the 1,4, 1 on this branch and 4 on that branch. Look at O prime being exterior to the pink family or magenta family. And then right here, when O prime is about to jump in, I'm about to go from the 0,4 to the, from the 1,4 to the 0,5 distribution. So now I have all vertices included over here on this branch. So there you have it. Okay. So we've seen. Oh yeah. So one last thing is, let's just tweak another degree of freedom here, which is the number of circles in the chain. So let's go back to a well-behaved initial kind of a situation here. Everybody's sort of ellipse inscribed, and there's no hyperbolas. There's just one combinatorics. Notice that, by definition, right? If O prime is interior to the inner Soddy circle, it's always going to be interior to the magenta harmonic family, right? Okay, so I never have jumping behavior here, as I did when O prime was exterior. Okay, so what do I want to show here? I want to show, for example, n equals 4. Here's n equals 4, and let's make this guy be well behaved. Let's look at what's happening to n equals 4. So there's 4 circles in the chain. The geometry is very similar to what we had before, but let's make a few comments about it. So notice what's happening to the cotangents of my pink harmonic family. We've shown this in the other paper, recent paper, that if the exponent to the cotangents in the sum is an odd number, the sum of cotangents, so the sum of cotangents proper is 0, sum of the cubes of the cotangents is 0, and we keep having the same kind of conservation in that all the exponents up until n minus 1 are conserved. The same is true for the orange family. I have 1, 2, 3, sum of half-angle tangents conserved, and the sum of half-angle tangents to the 4th power is not conserved. Let's see what happens with n equals 3. Here's n equals 3. Let's bring this guy back to the elliptic configuration like that. And let's look at what's happening to the conservations here. Let's animate that. I have 3 circles in my Steiner chain. I'm conserving in the harmonic family, I'm conserving the sum of cotangents proper, sum of cotangents squared, and not sum of the cubes of the cotangents. Same thing here is happening. I'm just conserving the sum of half-angle tangents for k equals 1 and 2 because now n equals 3, so I only conserve up until n minus 1. And we're actually going to dive into the n equals 3 case because here you can talk about triangle centers and very interesting loci. We're going to do this on a separate video. But here's the n equals 3 case. You get the same phenomena. Of course, if I play around with the position of O prime over here, which is interior now, I'm getting the ellipse. If I move O prime to the right, when O prime is exactly on the inner Soddy, I'm parabola inscribed, and you get this kind of situation. The outer Soddy degenerates, correct? So right here I'm at the degeneracy. So I'm parabola inscribed. So this is a family of parabola inscribed triangles whose inner Soddy is fixed and outer Soddy is aligned. I can do the same for the n equals 4 case. By the way, at the degeneracy for n equals 3, you got 2 neat things. The sum of cotangents is 2, and the sum of tangents is also 2. Okay. Now, I'm actually seeing something rather curious here. It looks like these values are the same, and I was not aware of this property. Is this always the case for n equals 3? Let's see here. Yes, it is. Whoa. So the sum of tangents and the sum of the sum of cotangents and the sum of half-angle tangents to whichever power is conserved, they are the same value for n equals 3. So there you go. This is a new property I wasn't aware of. And that's the beauty of experimental simulation-based mathematics, right? You're sort of sometimes bombarded with things that you would have never noticed if you're just working out the math. By the way, this is not true for n equals 4. Look at this. So for n equals 4, the values are different, okay? Same thing for n equals 5. The values, the conserved values, they are different. You get the conservations, but let's try n equals 6 to see if there's any coincidences happening here. Doesn't seem to be any coincidences, right, for n equals 6. This is a pretty interesting chain as well. And you can see here that you're getting conservation up and all the way up to k equals 5 for both quantities, but they are not the same numbers. So we're getting something rather interesting and peculiar related to the n equals 3 case. And here's the n equals 3 with the inversions where you actually now hyperbola inscribed. Let's scale this up a bit. And in this case here, in fact, okay, so this is an interesting note I want to make. Let's go ahead and animate that. You're going to say, oh, the sum of half tangents is not being conserved for any number. It actually is. What's happening is the following. Let's let this guy be, yeah. So notice that when I'm actually have all the 3 vertices on this branch of the hyperbola, I get conservation. But as soon as I jump to the other branch, I don't. In fact, this is an optical illusion. What I would have to do here is actually use negative angles if for any vertex that lies on the opposite vertex of the hyperbola. There's a good geometric reason for that. You're actually considering the sum of half tangents if you actually take the extension of this polygon as it's actually tangent to the caustic, and you have to actually consider the complement of these angles because the polygon that is remaining tangent is actually made up of the extensions of these sides. So if you do that, you actually get conservation here as we do when everybody's on the same branch. For example, right now, notice that these numbers are not changing while I'm in the same branch. Let's make this guy, yeah, I think I can do it like that. And now it's going to remain on the same branch longer. You can see here that while it's on the same branch, it's conserved, and when there's a little jump, I would have to use the sum of tangents of signed half angles. Now the cotangents are not affected by that because the magenta polygon is always nicely inscribed in a circle, so you don't have this sort of complex number change of branches where I have to change the sign of the angle. Okay, so this is the n equals 3 case, which is giving us this additional property that the three numbers are the same. So I have two families whose sum of half tangents and sum of cotangents are the same number. Anyway, I think that we got a pretty rich exposure to what's going on here. Then again, you know, with n equals 3, you can do a lot of experiments regarding the loci of its triangle centers, and we're going to do this in a following video. But I think we got exposure to many of the degrees of freedom involved here, right? You have this degree of freedom, which is the choice of O prime, which just basically places you in the elliptic configuration, the straight line outer Soddy, or the everted outer Soddy. Then we have this degree of freedom, which is the number of circles in the chain. Here's n equals 4. Okay, here's n equals 5. And we have a degree of freedom, which is, let's see, was there another thing that I could regulate here? So I can regulate the position of O prime. I can regulate the number of circles in the chain. And I think that's it. And then, of course, you know, we've mentioned that there are these two interesting families. There's a harmonic magenta family, which conserves sum of cotangents to the power of k, where k is less than n. And we have this other orange family connecting the centers of the circles in the Steiner chain, which conserves the sum of half tangents to the k for k less than n. I think that's basically it. I'll see you guys in the next video. Thank you.